Hello, everyone. Thanks, Joel, for the introduction. I'm Javier Redondo, and I have to say that I'm not at my best, but it's really delightful to be here on air to talk and to present a little bit this issue of Axion dark matter and a possible experiment that will perhaps in the future be able to find axions and find dark matter. So let me just start. So the title of my talk is Madmax, a quest for axions, a quest for dark matter. Madmax is the name of the experiment that we are setting up in Munich, but now it will have collaborators from other institutions, not only the Max Planck Institute for Physics in Munich. So now instead of, well, originally it was just called the Munich Axion Dark Matter Experiment, hence Madmax. Now it will be more like magnetized Axion Dark Matter Experiment because it's no longer only Munich. So here we are, and in the screen you see that this is an experiment that has definitely a lot to say with many mirrors, but it will only come at the very end of the talk. So let me just start with a little introduction on axions and Axion dark matter, and a scenario of Axion dark matter which I'm very interested about. So you might know that in the standard model there are two sources of CP violation. One is the complex. One is a complex value in the CKN matrix, and the other is related to the theta angle of QCD. There's an angle that defines what a specific vacuum among the infinite vacuums that one could write for quantum chromodynamics. And this theta angle is the angle that controls this CP violation. That is also and it is degenerate with another phase of the CKM. Well, let's say another phase of the Yukawa matrix of the Higgs. Yukawa interactions with fermions. So and probably this second source of CP violation we have not heard very much about, and it is because when one tries to go and measure CP violation in purely hadronic observables, like electric dipole moments of different nuclei, or hadrons or nuclei, yeah, strongly interacting beasts. So one finds that actually there has never been actually any CP violation observed in these systems. So actually the strong interactions, they behave just like they wouldn't have any kind of CP violation. So this angle is actually measured, or is just bound by the most exquisite experiments to be smaller than 10 to the minus 10. And the smallness of this value, which is, by the way, if it would be of the order of 10 to the minus 10, it wouldn't be the smallest parameter in the standard model, because the Yukawas of the neutrinos, or at least of the lightest neutrinos, are for sure smaller than this 10 to the minus 10. But actually, you have not measured this thing, and so it could be much smaller than 10 to the minus 10. And yeah, and for us, the smallness of the smallness of the Yukawas of the neutrinos is something that is certainly very unpleasant. That's why we invented the seesaw mechanism, right? To have Yukawas of order 1, and the effective Yukawa of much smaller, just because there's a suppression by a high energy scale. So yeah, this is what we have in nature, a value of theta very close to 0. So in principle, there's no problem of having this, but actually, Roberto Pecei and Helen Quinn in the beginning of well, end of the 77 or something like this. They had this. They realized that actually this theta equals 0 point is something. Well, it's a very special point, because if one computes the energy density of the QCD vacuum as a function of theta, one realizes that actually the point where the energy is minimum corresponds precisely to theta. So actually they had then this idea. So what happens if theta is in reality not a constant of nature of the standard model, but it's actually a dynamical variable, a field that can depend on time and position, of course. So then they immediately realized that actually this would solve the strong CP problem, because the theta field will, with time, will go to the minimum energy position, which is theta equals 0. So that's the idea of the axion. Of course, whenever you have now a dynamical field with a potential and a minimum, excitations around the minimum of the potential, they are just nothing but particles, and these particles would be the axions. So and then the idea of axion dark matter is very super intimately related with this mechanism. Essentially, I've already told you everything. So the idea is that now whatever the initial conditions of the axion field in the Big Bang, in the beginning of time, regardless of the initial conditions that the axion take at these initial times. So as time progresses, the axion field will go to the bottom of the potential, and then will come back and then perform oscillations. And because the universe is expanding, these oscillations will just dump in. So the amplitude gets decreased. And and with this, we can get a very small value of theta. But however, the prediction is that since the lifetime of the universe is finite, there will be always some oscillations, some residual oscillations of the axion field, so that in these oscillations there's some energy, and actually this energy behaves essentially like dark matter. Okay. So there will be always some dark matter. So in this slide, you have this picture of the dark matter, actually dark matter, and you have actually something that I think is very, very important. That this the theory of axions is really economical, in the sense that in principle one only needs one parameter, because theta is an angle, and it cannot be well. If you want to write a kinetic term for theta, you definitely have to include one energy scale, because a kinetic term involves fields with energy dimension equals 1. So this field with energy dimension equals 1 would be what we call the axion field, and this Fa is a new energy scale. And yeah, because this picture we know more or less very well, okay, with this potential, but this potential we know as a function of theta. And then what we know is as a function of A, right? Because it depends on this scale Fa. So we can, in particular, we can compute this second derivative as a function of theta. So the axion will have a mass, of course, and the mass of the axion is of course going to be inversely proportional to this Fa. Okay, very good. So one can study very relatively easy what is a dark matter yield as a function of the axion mass, which is what you see in this figure. And this is relatively surprising. First of all, because the axion has something to do with QCD. Essentially, it has the same quantum numbers than the theta angle, which are the same quantum numbers than the eta, or eta prime, if you want. So the axion mixes with eta prime, and it gets interactions with all the standard model, just like eta prime would have. In particular, it gets an interaction with two photons that allows this action to decay, for instance. But also through the mixing with the eta prime, the action becomes mixed with pions, and so the action can interact with pions. And in the early universe, you can just from pions produce axions. So then the first line that I want to just highlight to you here is this thermal abundance of axions as a function of the mass. So it increases just like just like the Lee-Weinberg curve for neutrinos. It increases, but at some point it decreases, and it's because this axion decay starts to be too important. So then with the thermal abundance, we never make it to the relic density today, okay? Which is here expressed in funny units, funny physical units like kilo electron volt per cubic centimeter. So, okay, however, if you go much smaller in mass, you see that there are different lines that go up here. And these are the lines due to a non-thermal production of axion dark matter, which is exactly what I was just telling you a bit before. So the idea is that these very small masses, the axions are so weakly interacting that actually the only thing that happens to them, or to the axion field, is that it evolves in its potential. So there's no important interactions that will change that will change the axion field. It will only be a relaxation towards a minimum of its potential. And here you can more or less understand what happens. So, but the most important thing here is that the final yield, as you can see here, first of all, the final yield decreases with the increase in mass. This is very easy to understand, and it's because so I told you that the dynamics they involve this new energy scale. Okay, so as a function of this energy scale, if this energy scale is very large, so this potential will become extremely flat, right? So the dynamical time scales for this axion field to go to the minimum will be much longer. Okay, so it will take much longer for the axion field to go to the minimum, and this means that the energy density that it has at the beginning, it will last for a much longer time. So that the residual oscillations today will be larger. So that's the reason why if you go to higher masses, which means smaller values of Fa, you get a smaller dark matter density. But you have here something more. You have different lines. Not only the slope is important, and this helps me to highlight something which is very uncomfortable, but is what it is. In this realignment mechanism, it is essential that the axion field is not disturbed by interactions with the rest of the world, and then this means that the initial conditions, they determine the final axion yield. So this is not like WIMPs that once they thermalized everything. Once they thermalized, there's no dependence on the initial conditions. Here, the initial conditions are important until the end. Okay, and there are two classes of very important scenarios. Two classes of very important scenarios. One which depend essentially on the type of initial conditions. One has a random initial condition in different patches of the universe which are causally disconnected. Okay, so this is what happens if the axion just appears as an angle after a phase transition, and for instance, it will lead to something like this. Okay, so this here you have in a two-dimensional slice of the universe after a phase transition in which the axion field takes values. Okay, I've written it as a function of theta, and here you see that there are different patches of the universe where the axion field, for instance, is already 0, which is black, and some other places is around pi, which is white, and of course some intermediate values. So if nothing happens after this picture, of course, these regions with in which the Axion field is more or less homogeneous are of the order of the size of the horizon at that time, because the information cannot propagate at longer distances. But of course, as the size of the horizon expands, okay, as the universe expands, as the light propagates, essentially, these regions will tend to be, of course, larger and larger. But today, these regions are still. So these regions increase at the speed of light until the axions become massive. So until the axion mass becomes effective, and then they just essentially contained. So the typical dark matter density in this scenario, it is a result of these stochastic random initial conditions, and it will have a coherence length which is related with the size of the horizon when the axion mass is important, and this is a very small distance compared with the universe today. So we will have very strongly inhomogeneous dark matter at very small scales. Okay. However, there's another possibility, which is that inflation takes place after this moment, and so the axion field takes its random initial conditions after a phase transition, for instance, but then inflation happens, and then one of these patches in which the universe was more or less homogeneous gets blown up to cover our entire universe. And then, in this case, we have no prediction for what the dark matter of the universe will be, because our universe could have been any of those small patches. We could have started with a very small amplitude or with a very large amplitude, and all these things will happen at the same time. So we lose the predictability. Okay. So essentially, in the first scenario, one can just make the numbers, and one finds that essentially, with a relatively large uncertainty, because we cannot do these numerical simulations very well at the moment, one gets that the full amount of dark matter will be obtained if the axion mass is something like 100 microelectron-volt. Okay, 10 to the minus 4 electron-volt. If the axion mass is larger, then we will not have enough dark matter, and if the axion mass is smaller, we will have too much. So this is excluded. There are other arguments to exclude axions with a mass of something like 20 times 10 to the minus 2. So these are astrophysical bounds. This is the scenario that I'm mostly interested in because we have a prediction. Okay, we have the prediction that axion dark matter should be here at the 100 microelectron-volt. On the other hand, if in this second scenario that I told you, in which inflation happens afterwards and selects one value of the initial conditions, then we can have we can just have the full amount of dark matter for any value below essentially 1 milli-electron-volt mass. Okay. The only thing that happens is that for very small masses, where we would have a lot of dark matter, typically, you have to tune the initial condition to 0, and for very small masses, you have to tune the initial condition very close to pi. But in principle, you can have them in, you see, for a very wide range of axion masses. Very well. So this was axions and axion dark matter in a nutshell. So let us try to see how can we detect these residual oscillations of the axion field. Okay. So the idea is very simple. So now we have the dark matter as the form of oscillations of a new field that you don't know very much about. These oscillations, they have to account for this 0.3 GeV per cubic centimeter of the local density of dark matter that we think we are immersed in. And the energy density in an oscillating field, non-relativistic field, is essentially the energy density of a harmonic oscillator, that 1/2 of the time derivative squared, 1/2 of the potential. Oh, sorry, the potential, which is 1/2 of the mass squared multiplied by the field. And we have harmonic oscillations around the minimum. So that you can just think that the axion is oscillating in time with a frequency which is given by its mass. So that actually these two terms are equivalent. The energy is equipartitioned between kinetic and potential. And essentially, if you write the action field as theta times Fa, then you find this ma squared times Fa squared, and this is nothing but the second derivative of the QCD potential at 0. And this is a quantity that we can compute. This is model independent. It comes from QCD alone, even if it involves two parameters of the action field. So the only thing that we have, knowing the energy density around the Earth, we can obtain the amplitude of the oscillations of the axion field, and they turn to be of the order of 10 to the minus 19. So you see, even if this is a very small number, and certainly is much smaller than the upper limit that we have for the electric, so for CP violation observables, like the electric dipole moment of the neutron, which is something like 10 to the minus 10. Even with 10 to the minus 19, we can just get enough energy to account for all the dark matter around us. Very interesting. So how can we try to measure the oscillations of the axion field at the level of 10 to the minus 19, 9 orders of magnitude smaller than the sensitivity to detect nuclear electric dipole moments? And the answer is we can do this because now the electric dipole moment, or any effect that theta will produce, is now going to oscillate in time, and it's going to oscillate in time with a very nice coherence length. The axion field is very coherent. So we will be able to use some kind of resonant effect. So here in this slide, you have some ideas that people had to search for axion dark matter. The most important is using resonant cavities, but we also have mirrors, LC circuits, spin precession, atomic transitions, and optical. I'm going to just show you in the next slide, more or less, since all these experiments use more or less some resonant effect, they all are very sensitive to the exact axion mass, which is the frequency with which the axion field oscillates. They are somehow very good in one mass range, but very bad in the others. So they are somehow scattered in parameter space. This is the oscillation electric dipole moments, so NMR techniques. These are LC circuits. These are the resonant cavities. Around 10 to minus 5 is the best spot. There are also not dark matter experiments that search for axions in different environments. And as you see, this is the region I want to cover, and it's only covered a little bit by, will be only covered a little bit by these cavity experiments. So Madmax is an experiment I'll tell you a little bit about now that will try to cover this parameter space. So the idea of detecting axion dark matter with these cavities and Madmax is the same, and it relies on the fact that the axion couples to two photons, as I had already told you. This is at least because of the mixing of the axion with the eta prime and through the eta prime to all the pseudoscalar mesons. If you want, you can write this term as a Lagrangian interaction term between two photons, which is B dot E. Okay, and the axion always divided by Fa. And then you have this relative correction that comes because this interaction comes from a triangle diagram, and then a model dependent coefficient of order 1. This is, of course, the axion field, and here we know that now this guy is oscillating. So the idea is very simple. If the axion field is now oscillating, it acts like a source. The idea is that if you put a very strong magnetic field that will be also part of the source, then this interaction term, this Lagrangian interaction term, will become just like a source. Will become a source for electric fields. Okay. So and you can read essentially from this formula the size of the electric field that it will be sourced by this oscillating source term, which is essentially the value of this current. And okay, so I've used that the theta of t, I can write it as theta 0 times the cosine of the mass multiplied by time, because this is the frequency at which the axion field oscillates. Very good. So let us continue. Let me just tell you about the resonant cavity experiment, which are the only ones that are taking data at this moment, and they have been the most important experiment so far. The idea is that once you get, you put a magnetic field, and the axion field is oscillating, so this generates an electric field. So the idea is that this electric field that is oscillating also in time can now be amplified inside of a resonant cavity, okay? In such a way that the output power, instead of being only proportional to the electric field squared, is now proportional to the electric field squared times the quality factor of the cavity. That can be as large as 10 to the 5. And then, because this is a resonant cavity, this is a cavity, then you have another factors, which these geometric and coupling factors are of order 1. But the important thing in this experiment is that the power that one can extract essentially is proportional to the volume of the cavity multiplied by the frequency, or by the axion mass. This is the output power when the cavity is resonant at the frequency given by the axion mass. Okay, and unfortunately, we don't know exactly what is this mass. So what these experiments do is just to tune the cavity. They measure for a few seconds. Then, if they don't find anything, they just retune the cavity to a different resonant frequency, and they continue. They measure and they continue. So essentially, what they do is just measure one frequency band at a time. Now, this experiment, you can see here the reach in this model independent parameter as a function of mass that different experiments have found. Essentially, only at the smaller frequencies is where ADMX, Axion dark matter experiment in Seattle now, has been able to reach values of order 1 that correspond to popular models like HVZ or TFSC. These are in color. You have the prospects, which are very optimistic, and you see that all the experiments that try to search for axion masses which are much larger than a few 10 to the minus 6 electron volt, they actually had a much worse sensitivity. And an explanation, you find it here. So the idea is that, first of all, the noise that you have to fight against the signal is proportional to the mass squared. And the signal is proportional to the volume, but in these cavities, the volume of the cavity is proportional to the wavelength of the frequency. So at higher frequencies, you have a smaller wavelength, and then your volume decreases. So that actually power out is also inversely proportional to 1 over the mass squared. So that's why this sensitivity of the natural experiment, it drops so fast, as you see. But okay, there are good ideas to improve all these things, but these values are still quite far from 10 to the minus 4. That's why we think that instead of improving this experiment, we could just try to avoid, we could just try to devise a different experimental concept to fight against the fact that our power out will decrease like 1 over m squared as we increase the mass. So one experiment in this direction, one concept in this direction was put up by some colleagues and I, what we call the dish antenna experiment. The idea was very simple. So just imagine that this, in a magnetic field, the axion field is exciting some electric field coherently. So then you just put a reflecting metallic dish, and then this electric field will essentially reflect or will induce currents, if you want, in the dish, and this dish will radiate. And now, if it's spherical and the wavelength of the light is much smaller than the diameter of the disk, there will not be very large diffraction, and all the power will be concentrated in one point. I will tell you a little bit more about this production mechanism. Well, the idea is that in this case, the power is proportional to the electric field squared that I told you before. This is a fixed electric field. Okay, it's not dependent on the dark matter. It's only dependent on the dark matter density, but not on the Axion mass. And it's proportional to the this is proportional to the electric field and proportional to the area. Now, if you have an area which is much larger than the inverse wavelength, you can just compensate with a large area the quality factor that these cavity experiments have. So that was the idea, but it turned out that it was not good enough. So let me just it was not good enough. So in the Madmax experiment, we have just improved a little bit this idea. And in order to understand this, we have to study a little bit more the emission of the emission that comes from this mirror. But instead of using a mirror, I'm going to use a general dielectric with a general dielectric constant. It can be also imaginary, so I can just use it to describe metal. So the idea is that this electric field is inversely proportional to the dielectric constant of the medium. So if we have two different media, the electric field induced by axions will be suppressed inside of a medium with a large dielectric constant. Whether it's real or imaginary is not important. So this mismatch of electric fields is actually not a solution of Maxwell's equations. That tells you that the electric field transfers to a surface, it has to be continuous. So the way that nature just have take into account that this field is oscillating. So the only thing that we can add to this solution of pre-solution of Maxwell's equations is just plane waves that go out of the surface, plane waves of the normal plane waves of electric field and magnetic field. Okay, electromagnetic waves of photons, such that the Axion field, such that the electric field is completely continuous at the interface. Okay, and this predicts that there will be some electromagnetic radiation, which is the electromagnetic radiation that we wanted to collect in this dish antenna experiment. But now we know that we can have something which is much more general than only a dish antenna, and we can try to use. So the idea of the Madmax experiment was not only to use one surface, but to use many of these surfaces, because now we don't have to use a metallic disk here. We can just use dielectrics that are somehow transparent to electromagnetic radiation, such that the axions will produce waves, but these waves will go through the next layers and so on, and they can even, if we place the dielectrics at the right distance, we can even get a coherence enhancement of the signal, because the optical path is the same. So what we do to characterize the power emission in these disks is just define this power per unit area normalized to the power that would be emitted from one disk. Okay, that is this 2 times 10 to minus 27 watt per cubic meter in a magnetic field of 10 Tesla. That's the benchmark, 10 to minus 27. So here you have an example of what happens if I put 10, 40, or 80 disks with an index of refraction of 3. Let me just go back. So the important thing of this, or the working unit of this multi-dielectric haloscope, is this one dielectric slab. Okay, you have to imagine this, but in 2 dimensions, it will be something like, for instance, a disk. And the thickness of this dielectric, it defines a frequency. Okay, so one half wavelength inside of this dielectric defines a frequency, and this frequency is the important one. This is the key frequency that tells you many things. For instance, the Axion emission, what we call the boost factor, is just the boost factor is the ratio of the power of this thing compared with a metallic disk. For instance, you see here that if the frequency is just much smaller than this, the characteristic frequency that corresponds to half a wavelength, there's no emission. It's like essentially this thing is transparent, and the Axion field doesn't emit anything. But very soon it goes up, and it almost reaches 1, which would be the metallic disk, and would be the maximum emission per unit surface. But here in this intermediate region is actually relatively large, so 0.8 and above for different indices of refraction. And here you have the transmission coefficient. So once this wave has been emitted, it has to go over other slabs of dielectric. So we want this is maximum, and we want the transmission also to be maximum, or at least to be large enough. We don't want to have a 0. And you see that actually the transmissivities are always, of course, they are at 0, 1, 2, 3. They are maximum of transmissivity, because here I didn't put any absorption. But there are some dips of transmissivity when essentially when you have 1/4 of wavelength inside of the dielectric. But in a sense, all the transmissivity is actually quite large for these values of the index of refraction. So once you put many of these disks together, and then you get a boost factor curve. So once of course you choose the interdistances. And then you can just look at the boost factor, which is the boost factor is this beta parameter here, essentially the power compared with the emission of one layer of metal. And you can see more or less that for 10, 40, and 80 layers, essentially around the central frequency that you have designed for, you get an enhancement of the order, which is 10 or 40 or 80. Essentially n times the number of disks times the boost factor of one dielectric layer. And the power will be proportional to this number squared. So with 40 or 80, you can get boost factors of the order of 1,000, which is fantastic. And this, so in this experiment, the boost will come due to the large area, and it will come from the fact that you can also put many layers at the same time. So you can have two sources of boosts. There's something interesting also, that when these layers are not transparent, you create something like small resonances. For instance, if I put here a mirror and only one dielectric disk, and I've set the distances such as this is a half wavelength and this is a quarter of wavelength, which corresponds to the maximum reflectivity. You have here that, for instance, with an index of refraction of order 3, for which we have a very bad reflectivity, but okay, it's of order 1, but it's not bad. We can get a boost factor that peaks at values which are of order 5 or 6, as you see, and this is to be compared with the emission of one disk, okay, or 2 disks if you want. So one can get a very mild boost of order 2, 3 if one gets these resonances inside dielectrics. Well, the nice thing about these dielectric haloscopes is that, well, in principle, we can choose the thickness and the index of refraction of these dielectrics, and then we can play with the distances between them to tune our experiment, essentially, right? So for instance, we can just get boost factors which are very peaked in frequency, okay? That will be boosting very much one frequency. If the action is here, it will give us a very large boost factor. But we can also adjust the distances in such a way that the boost factor gives us a smaller boost, but on a much broader band, as you can see, for instance, here. Okay, so that we can tune up more or less our scanning of the experiment. So we can do scanning all these frequencies at the same time, and then just move it, as you can see here. So we can do all these frequencies at the same time, and then we change again, and all these frequencies at the same time, etc., etc. But as if at some point we detect a signal and we want to specialize on that signal, we can just tune our experiment and to have a much larger boost factor, not of the order of 100, but of the order of 1,000. Okay, and with that, we could measure much better with much larger precision. So with this technique, by the way, so that the theory of how we deal with the emission of these layers and how we tune these devices was just put up recently in a paper that was accepted in JCAP, and also we put up a letter that has been accepted in PRL, so it will appear soon. I'll write the reference for you in the slides. So this is the potential reach that we think we can have. So in this very busy plot, you find the model-dependent axion to photon coupling of order 1 as a function of the mass, or Fa. So these are two scales giving you the same, or the frequency. This is just 2 pi divided by this. And this is just this divided by 2 pi. So you see here that what we think we can do with a dielectric haloscope of 80 disks, measuring during 5 years, which is the typical lifespan of these experiments. Although one can, in principle, could run for longer, but more than 5 years. Probably it calls for improvements in R&D. So this will consist on 80 dielectric disks with an index of refraction of 5. These materials exist, although it's very complicated. We still don't know how to make them of the order of 1 square meter, but okay, we are working on that. And a magnetic field of 10 Tesla, which at the moment there are essentially no magnetic fields of 10 Tesla that span 1 square meter. So all these things will have to work out, but they are doable, I think. So one cannot claim that this is impossible. It's just never been done because there was no need. So, but with that, in 5 years, we think we can just cover all this region at the level of the most important Axion models that have values of C of order 1. Okay, and reaching even not only 100 microelectron volt, but a little bit above. Very good. So let me just summarize a little bit. So why we think that it can work? So the idea is that we can have a very large volume, which in this case means large area, compared with cavity experiments. Also, the tuning is relatively simple because it's just one-dimensional tuning, so the distance between plates. We can have long measurements in broadband configurations, or we can have short measurements in narrowband configurations. We can just adjust this to the time that to the still unknown time of tuning of setting the 80 dielectrics, because we don't know how long will it take. It might take 10 minutes, it might take 1 day to adjust the dielectrics as we want. So with this flexibility, we will be able to compensate. What can go wrong? So yeah, essentially magnetic fields that give us 10 Tesla in 1 square meter aperture that they do not exist. Also having 1 square meter dielectrics, I mean, these are, you don't find them in shops, although we think that we can tile smaller pieces, but we are working on that. Tolerances, they actually look relatively good, but still we have to we have to keep errors at or let's say the thickness of the layers and so on at the order of 20, 50 microns, which is very much doable, but it's challenging when one talks about 1 square meter layers. And diffraction. Everything that I told you about has been developed in 1D because we are thinking that because the wavelength of the axion radiated electromagnetic waves is much smaller than the diameter. So we know that diffraction is going to be small, but how small is something that we are just working on that in the lab and also with simulations. So let me just conclude. I think the strong CP problem and dark matter motivate Axions very nicely, even if they are not a necessity, but they are a very beautiful solution of both problems. And the most predictive model has these 400, or most predictive because you cannot, so the initial conditions are just averaged away. It will have this axial mass of the order of 10 to the minus 4 electron volts. One can say that there are many experimental efforts, but there is a missing solid player at this range. And yep, so microwave emission, I've explained you how the axial field in a magnetic field can excite electromagnetic waves coming out of surfaces where the index of refraction changes. I've also explained that this emission is relatively weak, but that we can just enhance it by just putting many different layers of dielectrics one after the other. And this is essentially what is the Munich or magnetized axion dark matter experiment that I hope it will be taking place relatively soon. Certainly now, I mean, we are just working on that, and we are working on enlarging the collaboration to afford the many working packages that we have to develop. Essentially, the magnet and tiling of the dielectrics. Yeah, I don't know. When a theorist has one experimental idea, everything is very easy. When you mess up with experimentalists and they just break up the experiment, all the practical details you have to care about, then everything is a matter of 5 years. So more or less, these 5 years is the time that it might take to see our experiment in full glory. But we are having nowadays small prototypes of growing dimensions. So that's all. Thank you very much. Now, if you have questions, I'll be glad to answer.
Okay, thank you very, very much, Javier. It's been a very nice webinar. So before we start with the questions, let me remind everybody that you can make your questions via the live chat in YouTube, which is on the upper right. And you can also make some questions via Twitter, again, on this address. Okay, so that's it. You might want to know that we've had as much as 30 people watching at some point, just to have an idea of your audience, right? So let's have a look at the questions. Is anybody in the audience right now? Does anybody have a question?
I have a question.
Please go ahead.
Can you hear me, guys? So, Javier, I think it was on slide 8. You show that axion dark matter heavier than, say, 100 MeVs or milli-electron volt is excluded or something like this?
Mm-hmm.
Yeah, okay, but when it's experimentally excluded, or is that we really don't know how to produce it?
No, we know that it is produced too much. Sorry, you mean in this region here?
No, when it's heavier than 10 to the minus 2 EV. Yes, exactly.
Here, there is no problem with dark matter. The problem is that axions are too efficiently produced from supernova. So this exclusion has and it has nothing to do with axion dark matter. It's astrophysics. Actually, you can you can see here there's a bound from supernova 1987A, and also there are some other astrophysical bounds. So there wouldn't be any problem of having axion dark matter here. But in this scenario, in the scenario in which we have average initial conditions, we know that it has to be smaller than the relic density. So it will be 10% or 1%, something like this. I think, yeah, in this range would be smaller than 1% here.
Okay, I see. Thanks.
So any other question from the people here? I have
okay.
Oh, yeah, go ahead. Yep.
Sorry, I have a second question related. I think it was slide 24 or something like this, about the boost factors. So, yes. So, for instance, in this plot in the lower left corner, so the boost factor have super different shapes. So they only depends on the number of layers. That's all. That's the only thing that you're varying there.
It depends. So the only thing that we changed here is the distances between the layers, and it's not very clear how it is not very clear how to do it. But we can train a computer, and this is what we did here, to have a certain boost factor in a certain band. So we decided that we wanted to have, for instance, in 200 megahertz, okay, which is this band here, we wanted to have one minimum boost factor, and then so the computer can just find the distances between these layers that you have to put in order to have this response, okay? If you want to have, so if you allow to have a smaller bandwidth, then the computer can give you, let's say, you can tune the distances to have a larger boost factor, but always in this smaller range. And if the band is much smaller, yeah, the boost factor can be larger. But the only thing that we changed here is the distances between the layers.
Okay, I see. Thanks.
Essentially here, I think it also depends on the distance or the thickness of this layer and in the index of refraction. Here was about something like 3 millimeters, and n equals 5. But you can do it. You can do essentially this game of changing the distances, changing the broadband or narrow band of the experiment for any index of refraction and for any thickness.
Okay, fantastic. Any other question? So I have a very basic Axion question. So why do we get interactions that affect the EDM and not the magnetic dipole moment?
So I can answer very well. Maybe it's not that simple. So that's the theta. So the Axion field is just a generalization of theta, this CP violating parameter. Okay, so the magnetic moment is not CP violating. So you know that it cannot couple. You cannot couple theta to any magnetic dipole moment operator in the Lagrangian. So you cannot couple theta, but you can couple theta squared. And this is what happens. So you will have interactions with the magnetic moment, but you know that they are going to be suppressed, but not by 1 over Fa, but by 1 over Fa squared.
I see.
Essentially. But also, you know what the prediction that we have for the relic Axion oscillations today is of order 10 to the minus 19. If you make this thing squared, you know that this will be something like 10 to the minus 40. So that actually this is super small, super small quantity.
Mm-hmm. Okay.
If you want to couple something to the magnetic moments, you have to know that also these. So when you put in a magnet, but maybe this is not a very good idea. Sorry, because when you have in a magnetic field, or you can just put an electric field, an external electric field, and then your Axion field will generate a magnetic field that will interact with the moment. But of course, one has to see how you create this electric field.
Right.
But yeah,
okay.
At the level of the Lagrangian, these couplings are forbidden at linear order.
I see. And the other question I had is, so once this is built, once in 5 years, suppose that it's built, so then what is the timeline? How much do you think that the experiment needs to run? For how long does it need to run, such as you get a result or an exclusion?
Well, the good thing is that we can start whatever for the frequency that we want, and so you have seen. So this is my job. Essentially, this prediction here is very wide, right?
Mm-hmm.
So in 5 years, my plan is to essentially reduce it so that in a year we can be done afterwards. Unfortunately, if after that year we have not found the Axion, of course this doesn't mean that we are not going to find it, but then I cannot give any time scale because it can be anywhere, right? Mm-hmm. It can be in this scenario because these are two cosmological scenarios, right? So, so the initial conditions of the Axion field tell me what are related with the Axion mass today. Okay, so if we are in this cosmological scenario, I know that we have to be somewhere here, and I will narrow down so that these experiments are very easy. So once you find the signal, you find it in a matter of in ADMX. It takes 1 second or 2 seconds to find a signal. The problem is to know the frequency. Okay, in this case it will be the same, and I think in 1 year, so if I have a 10% or 10% prediction for the Axion mass, I can do in 1 year, okay? But if I don't find the Axion here in my prediction, then this will mean that either Axions do not exist or Axions took these very particular initial conditions after, because inflation gave only one initial condition, okay? And in that case, I have essentially, the Axion field can have any mass, and still I will have all the dark matter. In that case, I think we will run for another 5 years, and then we will have to give another webinar to tell you about further plans.
Okay, I see. So related to this, there's a question from the live chat from Shantanu D, who asks, at what point does Axion dark matter is ruled out?
Sorry, can you repeat?
So he asks, at what point can you rule out Axion dark matter?
We are very far away from that point. But so let me just, I think there will always, there are ways of escaping all the constraints that one can use to kill Axion dark matter, okay? But I'm going to tell you the two most important ways of ruling out this thing. So my argumentation is based on the idea that Axion dark matter takes initial conditions which are homogeneous thanks to inflation. So we are in this scenario, or takes these random average conditions. Okay, so there are only two of these options. Now, in the first option, the Axion field exists during inflation, and because it exists during inflation, it gets quantum fluctuations that are amplified to distances like we are probing with the CMB. And then essentially the Axion fluctuations, they become dark matter fluctuations that are imprinted on the CMB in the form of isocurvature perturbations, okay? Now these isocurvature perturbations we don't see. So they are a way to constrain the Axion field. Now, the size of these isocurvature perturbations is proportional to the Hubble scale during inflation. And this is something that we can measure in the future. At the moment, what we can always say is that these constraints do not affect because the Hubble scale during inflation was very small. But if a gravitational wave, so if we detect primordial gravitational waves with the next CMB probes, polarization probes, then we will know that the Hubble scale during inflation was very large. And this will mean that we will have huge isocurvature perturbations, and this scenario is ruled out. This will allow at least to rule this scenario in the simplest case, and then we are left only with this scenario. And this scenario has also other problems or other possible constraints. For instance, I think the easiest is just to do the experiment and rule them out, because here you only have to search in this region. But there are also some other interesting effects, like that I was telling you before, that in this scenario, the dark matter distribution is very inhomogeneous at very small scales, and this gives rise to what we call Axion mini clusters, essentially. So in this scenario, there will be a lot of small scale structure in dark matter. So there will be a lot of clumps of dark matter. Now these clumps, they can be in principle ruled out or find out with microlensing studies. There was a recent paper by Fairman and Marsh that they were saying that if the amount of dark matter in mini clusters is larger than 70%, is 30%, 10%, I think. If it's larger than 10%, then this scenario is ruled out, okay? Because they did some microlensing studies and they didn't find microlensers. So this scenario could be ruled out by substructure microlensing or just by a direct detection. But you see, for me, there's no. So these are the strongest arguments that could kill Axion dark matter. But you see that there will be a sequence of different arguments that will allow you to kill all these models. And to every of these arguments that I've given you, there are known drawbacks. But okay, this maybe is good for another question.
Okay, super. And there's one question coming from Paulo Silva, which is somewhat long. So let's see. So the Axion through the Peccei-Quinn mechanism was introduced to explain why theta is so small. When you come to the dark matter problem, it seems that the amplitude of theta, so theta 0, also has to be very small. So he's asking aren't you changing a naturalness problem for another and then washing out the original motivation of introducing axions if they are to explain the whole dark matter in the universe?
Okay, that's a fair question. So let me just rephrase it. So the idea is that, yeah, in the standard model, we have to explain why this theta is smaller than 10 to the minus 10, right? Now I'm telling you that a natural way to do this is just to invent the axion, because whatever initial value of the axion field, it will end up in 0. That's great. Now, if we go to the dark matter lens, to the dark matter plot, if I take a very small value of the axion mass, if I want to have the full amount of dark matter, you see what is happening. I have to choose an initial value, or nature had to choose an initial value of the misalignment angle, which is very small. Okay, this only happens, and that's Paulo Silva. This only happens if FA is very, very large. The axion field is very, very small, and we are in this scenario, in this pink scenario. Okay, this is what that's the reason I call here tuned anthropic. There are some anthropic arguments that tell you that this might be anthropically selected. So wrapping up the question, the idea is that if so first of all, in this scenario in which I can, or nature can choose the initial value of the axion field, you can see here from this diagram that the axion field has to be tuned to be close to 0, but this tuning is much, for getting dark matter, is typically much smaller than the 10 to the minus 10 that you have to tune for the strong CP problem, okay? Because so the energy density of dark matter depends with the square of this initial value. So then essentially, yeah, it is a square root tuning. But in that case, you are right that one can, one has to tune the initial value of the misalignment angle to get the dark matter. But this is not generally the case. So here's what we have to emphasize, that if FA is smaller, so if FA is of the order of 10 to the 11, something like this, then one gets the right amount of dark matter with a misalignment angle of order 1, or with just these random initial conditions. Okay, you're just making different patches of the universe have different values of theta at the beginning, and this is this is scenario, and nothing could be more natural than this. This is also this is my favorite scenario, and because of that, I mean you are taking the most natural and predictive initial conditions, and you are getting the full amount of dark matter. But this only works for one value of FA. And you might not like this. In this second scenario, you can have much larger values of FA, but then you have to tune the initial misalignment angle. But so just remember that the tuning is not as large as 10 to the minus 10 in any case.
Hello? Hello? Can you hear me?
Yes, very well.
I have a question which may be naive. In the case that you have this inhomogeneous distribution, could it be that the scale of homogeneity is so large that we may be in some kind of place without dark matter, and so maybe we don't detect it even though it's there? Mm-hmm. But what is the scale of these inhomogeneities?
That's a very nice question. So the scale of these inhomogeneities, we can just we can predict is of the so the size of this box is, if I remember correctly, something like let's say 1 parsec. It's a little bit smaller than 1 parsec. So this means that now you can imagine that in this parsec there are many of these regions that had a lot of that were around pi, they will collapse and they will form these, I don't know, just mini clusters, like small clusters of Axion dark matter, and there will be mostly vacuum in between them, right? So we will have in 1 parsec many large amount of these lists. So the answer to your question is, for instance, inside of the galaxy we have millions and millions of these small clusters, and there will be, of course, some remaining dark matter which is not in the form of clusters, but it can be. So I think at least one can estimate that at least 10% of the Axion dark matter will not be localized in Axion dark matter clumps. It can be larger, but we are working on this. We don't know the answer very well, but it could be that maybe instead of 100% of the dark matter that we can just detect on Earth at any time, it's only 10%, and the rest 90%, it is just in a collection of very of dense clumps, which actually they are not so dense, but they are much denser, of course, than distributed dark matter. And these clusters, even if they, well, let's say the estimate of collision with the Earth is something like 10,000 years or something like this. So we will not see. So we will not live to see one of these collisions, or well, let's say a dark matter clump going through the Earth. So this might be a problem for direct detection. That's why we are studying it a little bit in depth. But at the moment, I cannot tell you anything more. So, well, I think I already told you very much that your question is definitely a very important one, and that in no case all the dark matter is just inside all these clumps. So there's always a remaining 10%, something like this, which is outside, and at least one can just try to detect that 10%.
Okay, very good. I don't see any other questions. I don't know, anybody else? Apparently not. Then let me check. There's no more. There are no more questions on the live chat, and I don't know why I check Twitter, but I'm checking Twitter. And apparently, no, there are no questions on Twitter either. So I think that's it. Yeah. Okay. So thank you very much, Javier. It's been a fantastic webinar and a very good discussion. So let me remind everybody else that we're having our next webinar on the 1st of March. And if I am not wrong, I think it's Daniel Lopez who's giving the webinar, right? So we'll see you later. We'll see you by then. Thank you all for joining. And thank you, Javier, once again.
It's been a pleasure. Thank you very much.